Hello everyone, welcome to Z1 Tutorials. Today I am going to make a series over IR spectroscopy. In this spectroscopy, especially that is IR spectroscopy, you are going to understand the basic concepts of IR spectroscopy, and you are also going to understand how you can solve the IR spectra of various compounds, that is the application of IR spectroscopy. You will be able to understand how you are going to perform the experiments for the IR spectroscopy. Now let us start this spectroscopy, that is IR spectroscopy. If I am going to tell you that IR means to say, infrared spectroscopy, means to say we are going to use here the infrared region of electromagnetic radiations or the electromagnetic spectrum. Infrared region corresponds to the vibrational part of the electromagnetic spectrum, that is vibrational region, that corresponds to the vibrational transitions, that corresponds to the stretching and bending vibrations, that corresponds to the stretching of bonds or the bending of the bonds. Means to say almost all the compounds which have partially covalent bonds or polar covalent bonds that can absorb these radiations, that is IR radiations, and that the compounds can have these vibrations, that is stretching and bending vibrations. Means to say the bond can vibrate along an axis, in different axes, or the bond can stretch or bond can bend. Now if we will look toward the vibrational part of this electromagnetic region, then means to say that the energy of these radiations will be less than the energy of the visible region. You know very well that the visible region corresponds to the 400 nanometer to the 800 nanometers. Means to say I have the region, vibrational region, after this wavelength region. Means to say the energy of the vibrational part of this region or the infrared part of this region is going to be less than the visible region. You have understood very well about the electromagnetic spectrum. If I am going to supply the X-ray region or the X-ray wavelengths or X-ray radiations to the compounds, then that can break the bonds between the atoms. If I am going less than this X-ray, means to say I can supply the UV or the visible region. UV and visible region can supply the energy in the region so that there may be electronic transition. There can be electronic transitions in the bonds. Molecules can have electrons, and electrons can excite to the higher electronic energy levels. Therefore, the UV and visible regions can supply the energy corresponding to the difference between the electronic energy levels. Next, after this UV region or visible region, we can move toward the IR region or vibrational region. This is small part, correspond to the wavelength, specifically 2.5 micron meter to 25 micron meter. Micron meter is the basic unit for expressing these wavelengths, and some of the books you will see this micron meter is written in the form of only microns. Both the notations are same, means to say the micron is representing there in the micron meter. Do not confuse regarding that notations. This region can supply the energy in such a way that there is transitions between the vibrational regions. Means to say electron can absorb the energies and get excited to the higher vibrational energy levels. And when there is this excitations to the higher vibrational energy levels, then means to say there is stretching and bending of the bonds. The bonds can stretch or can show bending vibrations. After this region, specifically I am saying that after this IR region, we can move toward the microwave region, and microwave region, you know very well, it is lesser in energy from the IR region, then means to say the microwave region can supply energy less than the IR region. So the lesser energy levels, the smaller energy levels that are rotational energy levels can correspond to the that is microwave region. Means to say microwave region can supply the energy corresponding to the transitions between rotational energy levels. रमन स्पेक्ट्रोस्कोपी में ये रोटेशनल एनर्जी लेवल्स के बारे में काफी हद तक हम इसको पढ़ते हैं. नेक्स्ट अगर हम बात कर नेक्स्ट वी कैन टॉक अबाउट द लास्ट पार्ट दैट इज रेडियो वेव्स. This radio waves can supply the energy between the energy levels. Energy levels means to say we can supply the energy for the transitions between these nuclear transitions. Means to say we can show the transitions between nuclear energy levels by using these these energy radiations, because radio waves have smallest energies, and if we are supplying this energy, then we can show the transition between the nuclear energy levels that correspond to the spectroscopy that is called as NMR. Even we can supply this energy for the electronic spin transitions. We can supply this in the form of electronic spin transitions. Means to say we can study this region that is radio wave region specifically in EPR, electron paramagnetic resonance spectroscopy also. Next I am going to tell you that now we will use the wavelengths in terms of wave number. I have told you that we are going to use 2.5 micron meter to 25 micron meter region of the electromagnetic spectrum. Now we will convert this wavelengths into wave numbers. Why we are converting this, we will tell you after this explanation. How can we convert this wavelength into the wave number? You know very well the wave number is the reciprocal of wavelength. Means to say, now I am writing it here, wave number in terms of nu dash. If it is written in the nu dash, then nu dash will be equal to what? And specifically, please remember that nu dash is represented in terms of centimeter inverse. I am going to represent this nu dash into in terms of centimeter inverse. I am going to use wave number in the whole series. This IR specifically, I am going to use this wave number in this IR series. I will tell you there will be absorption, and I will tell you the absorption in terms of wave number, not in terms of wavelength. Reason I am going to explain later. Just understand how I am going to convert this wavelength into wave number. We know that nu dash is equal to inverse of wavelength, means to say 1 over lambda. Lambda is represented in terms of micron meter. Means to say we can write it as 1 over 2.5 micron meters. We know that is micron is equal to 10 raised to power minus 6 and meters is equal to 10 raised to power 2 centimeters basically. Then we can say that this micron meter is converted to 10 raised to power 4 centimeters. Means to say we can write 2.5 micron meter in terms of centimeter. How? 2.5 into 10 raised to power 4 centimeters. Now very simple. Now convert this 10 raised to power 4 minus form into plus form. We can take it in the numerator. Then this whole relationship changes to 1 over lambda. Lambda means to say 2.5 into 10 raised to power 4. Now you can calculate this value. You know that if I am going to put this value 2.5 into this expression, then I will have the wave number 4000 centimeter inverse. And if I am going to put this is 25 micron meter here, that is value lambda 25 here, then the value I am receiving here is 400 centimeter inverse. Means to say if I am going to represent the region 2.5 micron meter to 25 micron meter, then we can write it as that 4000 centimeter inverse to 400 centimeter inverse in terms of wavelengths. In terms of wavelengths, increasing wavelength, 4000 centimeter inverse to 400 centimeter inverse is increasing wavelengths.
Now let us understand why I have converted the wavelength into the wave number. It is converted into the wave number because of convenience purpose. Actually, the wave number is in direct relation with energy. Means to say, if the bond require greater energy for stretching or bending, then there will be greater value of wave number that is required there to show this transition or to supply that amount of energy. If I have lesser energy stretching or bending vibration, then the value of wave number will also be lesser. Then therefore, for this convenience, I am utilizing the wave number. Second thing, by using, in some books it is also shown that this, when I am using this wave number, then the range of wave number is increased. Why? You know that at first we are using 2.5 micrometer to 25 micrometer region. Means to say, in that case, there is only small ranges of wavelengths, but in terms of wave number, these ranges increased from 4000 to 400 centimeter inverse. That is also the reason that I am utilizing, or the books are utilizing, the wave numbers. Next is principle of absorption of IR spectroscopy. How IR radiations are absorbed by the molecules or the bonds inside the molecules. Like other spectroscopy, the IR spectroscopy also a type of absorption spectroscopy. Means to say, there is absorption of IR radiations. Means to say, there will be two energy levels. One is lower energy and second will be higher energy. But the energy level that will be here, that will be vibrational energy level, not other, that is electronic energy level, because we are going to use the energy difference between around 40 kilojoules per mole. 6 to 40 kilojoules per mole. Means to say, the energy difference of vibrational energy level is around this range. Therefore, means to say, if I am going to supply the energy from the IR radiation, then there can be excitation of electrons from lower vibrational energy level to higher vibrational energy levels. Now, whenever there is transition between these vibrational energy levels, then there is stretching and bending vibrations. Means to say, as soon as electron is going to excite from from lower to higher energy level, then there is stretching vibration or bending vibration. This excitation corresponds to stretching and bending vibrations. Now let us start understanding the natural vibrational frequency of the molecule or the bonds. You know very well, every molecule or every bond inside a molecule possesses a natural vibrational frequency. Means to say, it will vibrate on a definite vibrational frequency. If I am going to supply that vibrational frequency to that molecule, then it is going to vibrate. It will show the vibrational motion. Or vibrational motion means to say stretching and bending motions. Next, if I have supplied that radiation to the molecule, the bond will vibrate and will stretch like a spring, as shown in the structure. And second thing, please do remember, whenever I will supply this radiation, then the amplitude of vibration increases. The bond that is going to vibrate, their amplitude increases the vibration of that molecule or the amplitude of that vibration increases. Another thing that I am going to tell you that not every bond inside a molecule is going to absorb these radiations. Why? Because there should be a coupling phenomenon between the radiation and the natural vibration frequency of the bond. And this coupling phenomenon can take place only by means of if the bond has the dipole moment that is changing with respect to time. Means to say, if a bond has a dipole moment that is changing with respect to time, then and only then there will be absorption of that radiation and there will be excitation of electrons from lower to higher energy levels. What happens there? Basically, when the dipole moment of the bond that is changing with respect to time that couples with the sinusoidally changing the electric field of the radiation, then there is resonance. Then there is the absorption of energy. And during this absorption, then there is excitation of electron from lower energy level to higher energy level. What I said? I said that if a bond is possessing a dipole moment that is changing with respect to time, only then the sinusoidally changing electric field of the radiation is going to couple with this electric dipole moment of the bond, and there will be absorption of energy and there will be excitations and there will be various vibrations, or that there will be stretching and bending vibrations. Now let us understand this concept here. I have mentioned an example here, hydrogen and chlorine. You can easily see here that hydrogen and chlorine both have non-polar bonds. Means to say, if the bond inside the molecules are non-polar, I am going to supply the radiation. There should not be absorption in the radiation from what? That is the IR region. And we see here that there is no absorption of radiation. Means to say, the molecule which are not polar, that will not absorb the IR radiations. The basic principle behind the IR spectroscopy is only this one, that only those molecules is going to absorb the IR radiations which have net dipole moment. And second thing, please do remember net dipole moment of a bond. I am saying that net dipole moment of a bond means to say, if a bond has minimum one that is net dipole moment, then and only then it will absorb the radiations. Second thing, there is another example here. Some of the molecule I have represented here. One is symmetric and other is pseudosymmetric, closer to symmetric. These type of molecule is also here not capable to absorb these radiations. These molecules also are not capable to absorb these IR radiations. Means to say, if a molecule is possessing zero dipole moment inside the bonds, or you can say a complete overall dipole moment of the molecule is zero, or a little bit dipole moment, then also the molecule is not going to absorb these IR radiations. Means to say, we cannot analyze these compounds inside the IR spectroscopy. Please do remember, if a molecule is possessing the dipole moment and their bond has certain dipole moment characteristics, then and only then there will be absorption of IR radiations. Vibration should correspond to change in dipole moment with respect to time, and that vibration is going to absorb these radiations. This is for now. Next time we will understand what type of compound we analyzes in IR spectroscopy. Uh, but very little description. So we will have certain ranges through which I will explain the molecules that have certain functional group that will absorb these IR radiations. So in this lecture, I told you that in IR spectroscopy, specifically in mid IR region, that is vibrational region I have mentioned here, that has a range in 2.5 to 25 micrometer. I am going to utilize this region of electromagnetic spectrum for the analysis of IR spectrum. Second thing, I told you that there are other radiations also, other regions also that can be utilized for the absorption spectroscopy, but I am not going to analyze that. I'm going to analyze only small portion, that is vibrational or the IR radiation region, that is the mid IR region that correspond to 2.5 to 25 micron meter, or that is 400, that is 4000 to 400 centimeter inverse. Second thing, I told you that how you can convert this wavelength into the wave number. And third, we understood very well that how this absorption occurs inside the IR spectroscopy or various inside the various molecules. So hope so you like this. If you like this, please do share, do subscribe, do comment. Thank you for watching. See you next time.